Hi, Taylor.
Hello.
How are you today?
How's your day going?
Good,
Good. How about you?
good. So let me guess. I'll bet we're on half angles today.
Actually, no. We're just gonna be like pretty much tomorrow. We're gonna take a quiz, so I'm trying to just review over.
Okay.
Um, so pretty much, I just want to keep going over double angles and stuff
Okay.
like that.
Go ahead and you read it and we'll solve it.
Okay. 1 second. Okay. So sine x equals 4/5, and then it's in the second quadrant,
Okay.
and sine 2 theta.
You want to know what that is?
Um, 2 sine and cosine.
I lost you. Let's see. They want to know what sine 2 theta is?
Yes.
In addition, cosine 2 theta?
Uh, yes, that too, and cosine.
Okay. First of all, what's the general identity for sine 2 theta?
Um, 2 sine times cosine.
Huh?
Oh, I have to draw the triangle, right?
Well, that's the next step. In other words, in order to solve that, we know what sine theta is, they told us. But
Yes.
we don't immediately know what cosine theta is.
Correct.
So, whenever they give you one trig function and they tell you what quadrant it's in, this is always the first step. Draw a triangle labeled theta. Now, dimension that triangle for me.
Sine would be positive.
Well, first of all, what are two of the sides? You know two of the sides from that.
So AFPC. So
What's the
what I
side
know.
opposite theta?
Oh, 4/5. Yeah. So then the opposite's 4, and then the hypotenuse is 5.
Okay.
That's a 3/5.
Now use the Pythagorean theorem to solve for that, so you get 3. Now you know what the cosine of theta is. What's cosine of theta?
Jason over hypotenuse. 3/5.
What's its plus or minus sign
It's a minus.
in the second quadrant? So now we have the sine of 2 theta equals 2 times what?
So then it would be 4/5 times -3/5. So then 8/5 and -24/25.
And the fact that it's negative, think for a second. If we're talking about the sine of 2 theta,
It has to be positive.
it does have to be positive. Where'd we go wrong here?
I think it's because in cosine it would be negative in that quadrant, and then that's where I came up with the negative.
Well, now hold on a second. If if sine of x equals 4/5 or theta, whatever, and they say theta is in the second quadrant, well, then the sine of 2 theta is going to be either in the third or the fourth quadrant, right?
Yes.
In other words, the second quadrant angle might be 150 degrees. Well, so the sine of 2 theta would be 300 degrees, would be 2 theta, and that should give us a negative answer. So that negative sign is correct.
Okay.
Okay? It just, you have to be, you got to be a little careful In other words, the smallest that theta could be, or x, excuse me, is 91 degrees, right?
Yes.
Well, what's 2 times that? 182 degrees. That puts it in the third quadrant. So 2 theta is in the third quadrant and should have a sign of negative.
Okay.
Okay?
Yes.
All right, what else you got?
I also have to find cosine as well.
Oh, cosine of 2 theta, that's right. So we know the sine of theta and we know the cosine of theta, right? Sine of theta was 4/5. Cosine of theta was minus 3/5. Well, we've got our choice of 3 different identities for cosine of 2 theta. Now, since we know both sine and cosine, the simplest is probably the first one. It's the easiest to memorize, which is this. And the reason I consider that the easiest to memorize is because it's so opposite of the Pythagorean identity, which is cosine plus sine equals 1. So I never have any trouble at all memorizing this one. The other 2 I have a little bit of trouble with. You should remember.
Could I always use that one?
Negative signs in both of them, and the first one starts with 2 cosine squared. And the second one starts with 1 minus 2 sine squared. Okay, so that's how I memorize all 3 of them.
Okay.
Well, we can use any of the 3. It might seem like this one's the easier or this one's the easier, but we know what cosine is and sine. So I say let's use the first one. What's cosine squared of theta?
Cosine, so adjacent over hypotenuse, so 3/5 squared 9/25.
And that's positive. What's sine squared of theta?
Sine is so opposite over hypotenuse. So that would be.
Well, they told us what the sine was right there. That was part of the given.
16/25.
Right. So the cosine of 2 theta is also negative, but that makes sense. If it's in the third quadrant, it would be negative. It's possible that theta could be an angle such that it might be in the fourth quadrant, so it could be positive or negative. But in this case, we know that 2 theta has to be in the third quadrant.
Okay.
And theta here is 53 degrees. In other words, whenever you have a 3, 4, 5 right triangle, it's occasionally useful to know what that angle is, even though you rarely do. You will rarely have a teacher teach you what these angles are. I mean, they focus on the 3, 4, 5 triangle all the time, but they rarely talk about what theta is. Well, it turns out that theta is 53 degrees, that angle's 37, so 2 theta would be 106 degrees, second quadrant, cosine of 106 degrees would be negative.
Okay.
This isn't a bad thing to memorize, because a lot of these trig problems tend to be based on the 3, 4, 5 triangle. So if you know what these angles are, it can be a little helpful towards checking your answer.
Okay, I'll keep that in mind.
Was that it? Just sine of 2 theta and cosine of 2 theta?
Yes.
Okay.
And then also, what's the identity for tangent in case she does that for extra credit?
You want the tangent of 2 theta?
Yes.
It's a little like, well, I don't know. Everybody has their way of memorizing things. That's what it is. You can memorize it however you want. The numerator is pretty easy to memorize. But anyway, that's what it is. So if they were to give you the sine of theta equals 4/5, you would have to first figure out what the tangent of theta is. What's the tangent of theta going to be?
So total opposite over g. So then that would be 4/3.
Okay. Now we have the trig functions. We can plug in directly into that. So it would be 2 times 4/3.
8/3.
All over 1 minus 16/9. So that's 8/3 divided by minus 7/9. Flip and multiply, and you get minus 24/3.
Okay. Thank you.
Yeah.
I pretty much have the triangles down packed. The only ones I noticed that I understood the other day, but I completely blanked out on these today, were, I'll give an example.
Okay.
So sine 2x equals negative sine x within 0 and 2 pi.
Okay. What's the first secret for solving trig equations?
Identities and getting things
Getting
in the right
everything in the same angle. I can't work with 2x and x. I have no way to solve that. If I can get everything into x or 2x, then I can solve it. So the first thing we want to look for is the identity for that. What is the identity for that?
2 sine times cosine.
Notice we now have everything in x. Right? We got rid of the 2x, and that's what's important. Now how do we solve this?
Add sine x to the left.
Good. That's much better than dividing both sides by sine x.
Yes. And then I can factor out sine.
What do you have left?
Then I'll have 2 cosine x plus 1.
Now solve that.
So then sine equals 0.
Sine x equals 0. Where does that put x?
It'll put that. I remember. Oh yeah, it's on both the right and left side. That'd be pi.
The best way to memorize or to answer that is to be able to draw that curve from memory.
Oh yeah, I remember doing that.
Okay, and that goes to 2 pi, which means that's pi. So where is sine x equal to 0?
On 0 and pi. 180 degrees and 0 degrees and 360.
Correct. Okay, so there's a big value in knowing these two curves. It really is. Because they're forever asking you about sine x and cosine x, and cosine x is equal to 0 at pi over 2 and 3 pi over 2. So if you can draw these curves from memory, then you can always answer these questions relatively easy about the quadrangles. These are called quadrangles, multiples of 90 degrees. Okay? It's hard to get those from the two triangles that are 30, 60, 90 and 45, 45, 90. What's the rest of this? What's
Then
x?
2 cosine x plus 1, or 2 cosine x equals -1, then divide everything by 2. Then it'll be cosine x equals -1/2.
Where does that occur?
2 pi over 3 and 4 pi over 3.
And this answer you get more from memorizing these two triangles. In other words, because these are multiples of 30, 60, or 90, we basically get these angles always from these two triangles and the unit circle formulas we have. But whenever it's a multiple of 90 degrees, the only way to really get it is either from what you've memorized the unit circle to be, or knowing what the graph looks like. And that's the way I like the best, because you have to know what that graph looks like for an awful lot of problems. So the sooner you memorize it, the better off you are.
True.
Okay.
Next one I have is sine 2x plus 2 cosine x equals 0.
What are we going to do here?
2 sine times cosine.
Okay, what's this identity?
Isn't that the 2 cosine times?
2 sine cosine.
Mm-hmm.
And we've switched the 2x into x's. Now we can solve it.
So then I factor out 2 cosine. So then that'll bring me to sine, 2 sine plus 1. So then after that, 2 cosine x equals 0, divide everything by 2. Then that'll make it 0, so cosine equals 0. And that'll be located at pi over 2 and 3 pi over 2.
Okay, the rest of it?
Give me 1 second, I'm trying to write this all down real quick. Okay, then for sine, so then subtract 1, then divide it by 2, then it'll be sine equals -1 over 2. And that'll be located at 7 pi over 6 and 11 pi over 6.
It's good. Do you actually have the unit circle memorized, or do you use another technique? Because you're pretty quick at coming up with these angles.
Usually I draw the triangles when I do these, just as a point of reference. Like, I have it memorized. Like, this is what happened. Our teacher gave us a quiz, so you had to memorize it. And so whenever I do problems, I always draw it out and then look at it after that.
Okay. Well, whatever technique you're using, it's working, because you're as quick as anybody that I work with on coming up with these angles based on what, the sine and cosine is.
Mm-hmm.
Okay.
Yeah, in the beginning of the year, we had a big quiz on it.
Mm-hmm. No, it's definitely a good skill to have. And it's a difficult one, because learning trig is a little like learning Greek. It's like a foreign language. So memorizing all this stuff is doubly difficult.
Yeah, definitely. I noticed. The next one I have is... let me find a cosine. Okay, cosine 2x plus 2 equals -4 cosine x minus 2 cosine squared x.
Okay. What's the first goal?
we have to bring everything. When do you want to get everything on the same side?
Well, that's the second goal. The first goal is get all of our angles the same. Right now we have a 2x and we have an x. So the first thing we need to do is to get everything in either x or 2x.
So what I could do is 2 cosine squared minus 1.
The second goal is going to be to get everything in the same trig function. In other words, the two previous problems didn't have that. They were linear in nature, so that when we factored them, we could solve them. But once we substitute for cosine of 2x, we're going to have a quadratic in cosine as long as we use the proper identity.
Okay.
So what identity should I use for the cosine of 2x? In other words, this is a marginal degree of difficulty higher than the previous problems. Previous problems, there's only one identity you can use for sine of 2 theta. But for cosine of 2 theta, you got three choices. And it's important to choose properly, otherwise the problem will be a lot harder.
The one I have memorized easily is cosine squared minus sine squared.
Problem with that is that's then going to leave us with cosine and sine. We want to have everything in cosine if we can.
2 cosine squared minus 1.
Yeah, 2 cosine x minus 1 squared, That's the other identity for cosine of 2x. Now watch what happens. Now I have a quadratic in cosine squared x. And how do you solve quadratics?
Square root.
Put everything on one side, 0 on the other. In other words, the same way you would solve a quadratic that was a polynomial, not trig.
Add everything to the left side.
Okay, let's just bring everything to the left side.
So plus 4 cosine x and plus 2 cosine squared x.
Plus 4, I think, cosine x.
Cosine squared x.
In other words, all I'm doing is bringing this over to the left side. That's how I got 4 cosine squared x. And then I'm bringing this over to the left side. And that's how I got 4 cosine x.
Okay.
I still have the minus 1 and the plus 2, which combine that. And I'm left with 0 on the other side. That's always my goal when I'm doing a quadratic. Not always, but when I have a quadratic that has a squared term, a non-squared term, and a constant, then this is the way I always solve it. I set it equal to 0 on one side. If I have a quadratic that's like this, well, I don't have the middle term. I can solve that by taking the square root of both sides. In other words, I can leave the number on the right side and take the square root of both sides, so that I get cosine x equals square root of 3 over 2 plus or minus. You see the difference?
Yes.
In other words, if this one does not have the x term in it, so I can solve it in this manner. But if I have both the squared term and the non-squared term and a number, I have nowhere to go with that. There's no way I have a greatest common factor, okay, because the number is 1. So I have to factor it just like I would factor a polynomial. In other words, how would you factor 4x squared plus 4x plus 1?
Is that when we have the whole middle term thing?
Well, however you would factor this, you want to factor this exactly the same way. If it helps you, use this. Let x equal cosine x. Use that substitution. And then I will have 4x squared plus 4x plus 1. But you don't need to go through this step. You can just think of this as a quadratic in cosine x instead of a quadratic in x.
Okay.
How would you factor that? If that was 2x squared plus 4x plus 1, what would it factor?
So, wait. 2x squared, you said?
No, go ahead and try to factor it in cosine.
Okay.
This is an important step. I'm going to give you a hint. That's going to be 2 cosine x, and that's going to be 2 cosine x. Okay, and as all I've done is split that up, such that that multiplied by that gives you that first term. What are the signs? What do both signs have to be?
Plus 1.
Well, they both have to be plus. That's the second step in factoring. And then we want factors of 1. Well, we don't have much choice there. And now the question is that produce this middle term? In other words, is this the proper factoring? In order for it to be correct, it has to produce this middle term, does it?
Yes, it does.
Yeah. So that factoring is correct. I can now say all of that's equal to 0. And now what can I say about cosine x?
2 cosine x equals 0. No. Okay, ignore what I just said. Equals -1. Then after that, it's cosine x equals 1 over 2 negative.
Okay, cool. I tend to skip a couple steps after we do this over and over. In other words, what I'm really doing is setting that equal to 0 and solving it. Okay, and I get this. And where does that occur in the unit circle?
That occurs at 2 pi over 3 and 4 pi over 3.
Okay. So when you're substituting for cosine of 2x, consider what else you have in the equation. We have nothing but cosines. If I had nothing but sines, let's say I had sines over here, well, I'm not going to use this identity. I'm going to use the identity that says 1 minus 2 sine squared x, so that I will have all sine x's in my equation.
So you pretty much try to make everything the same.
Yes. You have to make everything the same angle, and you have to generally make everything the same trig function. Not always. In other words, we solved some like this, where I ended up with cosine and sine, and I was able to solve it, only because I was able to make it the product of cosine times sine. But when you have a quadratic like these, you're not going to be able to factor that unless they're all the same trig function.
Okay.
In other words, if just when you see something that's going to be cosine or sine squared, you want to get everything to be the same trig function generally, especially if there's a constant. In other words, let's look at this equation right here, okay? If I take away that 1, now it's a different story. I don't have to factor it based on my factoring ability. I can take a greatest common factor out of 4 cosine x, leaving behind cosine x plus 1, and now I can say, well, either that's 0 or that's 0. In other words, I don't have to factor it like a typical factoring problem. It's a greatest common factoring problem. And
So
I can
then,
do that whether those are the same or not. In other words, I was doing that when I had combinations of sine and cosine. I was able to do a greatest common factor. But if you have to use the quadratic to factor it, in other words, if you're looking at a quadratic where there is a constant, the moment you add a constant, you can't do any other kind of factoring here. I've got the squared term, I've got the non-squared term, and I have a constant. That is the definition of a classic quadratic. And here, let me make it just a little harder for you.
okay. So would I rarely use the formula for cosine where I have sine and cosine in it?
Well,
And these
you can always get to there from that. In other words, if this is the only thing you remember,
yes.
that's okay because you know what sine is, right? Sine is 1 minus cosine. So if I go in there and substitute 1 minus cosine squared, what do I end up with? I end up with 2 cosine squared of x's minus 1. So I can get to that identity even if that's the only one I remember. As long as you remember the Pythagorean identity. Sine squared plus cosine squared equals 1. And that's more important to remember than the cosine of 2 theta, to be honest. The Pythagorean identity comes up a lot more often. So like I said, if you know even one identity, as long as you know the Pythagorean, you can figure out the other two. And you actually would have gotten by substituting sine squared there, or cosine minus sine squared, because eventually you're going to have to substitute for the sine squared, and you'll end up with everything in cosine.
Okay. But I don't have to do it that way, right? I can just use the normal formulas that have the same
Yeah, the best way is to memorize those identities.
So it just matches up with it from the get-go.
Yes. Saves you a step if you do it that way.
Okay. I like it better that way.
Yeah, no, you always want to do these things the most efficient way possible.
Because it limits the chance of messing up, too.
That's right.
This one I have cosine 2x equals negative cosine squared x.
Which identity do I want to use for that?
Would it be 2 cosine squared x minus 1?
Now what?
Then I would add cosine squared x and bring it to the left side. Then I could do square root.
Not yet.
Okay.
Before you do square root, you have to isolate cosine squared x.
So then I would add 1 to the other side.
Yeah, this is a case where we don't have a cosine of x involved. All we have is the cosine squared and a number. So we want to solve this not by factoring, but by doing...
Oh.
Okay, that's the next step. Now I can solve for it by taking the square root of both sides.
Okay.
In other words, cosine x is going to be the square root of, well, 1 over root 3, which is same as root 3 over 3. And where does that occur? Don't know, do you?
Yeah, it doesn't exist. Undefined.
Well, it exists, but you have to use a calculator to find it.
Okay.
In other words, it's not one of your common angles. In other words, if I try to find where that is, well, there's x, cosine is 1, there's root 3 there. That means this has to be square root of 2. So I have no idea what that angle is. This is a odd triangle. It's not a 30, 60, 90, and it's not a 45, 45. So whatever x is, if it's not one of those common angles, in other words, if it's not a multiple of 30, 45, 60, or 90, you pretty much have to use a calculator to come up with x. It's the only way to do it, unless it happens to be a half angle or a double angle, and then you could do it that way. But I'm putting this in a calculator. In other words, I'm taking x as the inverse cosine of root 3 over 3. Put that in a calculator and it'll tell you what the angle is.
Okay.
Okay, but notice the difference. This was not a typical quadratic. This was a quadratic missing the middle term. And you solve those differently than you solve typical quadratics. In other words, you don't solve them by factoring, you solve them by taking the square root of both sides.
Yeah, I've never seen anything like it. Yeah, it's weird.
Well, it's kind of similar to this problem. Wow, what happened? I lost my... In other words, there's really not much difference between trig functions and polynomials. How would you solve that?
Square root.
Well, first of all, you got to isolate this before you take the square root. In other words, if I take the square root of both sides now, that's not helpful.
True.
Okay, because I'm not putting x on one side. So divide by 3 first, and now you have that isolated. You can take the square root of both sides. It's no different with trig functions. You're solving all of these trig functions the same exact way you would solve quadratic polynomials. And in fact, I was going to mention something here. Let me do it before I forget to. You may have to use, say I had this, sine squared x plus sine of x minus 3. Okay? I can't factor that. There are no factors that are going to produce the middle term.
True.
So how would I solve it?
Could I move the 3 to the other side first?
No, that's not going to help. In other words, if I move the 3 to the other side and then factor out a sine, the left side will have the product of two things, but it'll be equal to 3, which is not helpful. I can only solve if the product of two things is equal to 0. So I have to use the quadratic formula here. Just like if I gave you this problem and I said solve that, you would use the quadratic formula, right?
Yes.
X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay? Well, if I'm using this to solve this trig function, what goes on the left side of the equation? Is it x?
Yes.
No, it's sine x.
Sine x?
Yeah. In other words, this is a quadratic in sine x.
Okay.
N, a quadratic n sine x, which means if you're using the quadratic formula, you're solving for sine x, not x. Once you get a couple of solutions for sine x, then you can find out what angle you're talking about. You can solve for x. But it's very important, if you have to use the quadratic formula, to know that the left side is sine x. So what would sine x be equal to here?
So it would be equal to sine plus or minus sine squared.
Hold on. Remember, A, B, and C are the coefficients only.
So then it would be 1. Negative 1.
Plus or minus?
1 minus 4 times 1 times negative 3.
All over?
2.
So the sine of x is equal to minus 1 plus root 13 all over 2, or the sine of x is equal to minus 1 minus root 13 all over 2. Now, one of these may be impossible. You don't have to consider it. What's the range? What's the range on sine of x? What's the biggest it can be and what's the smallest it can be?
The biggest it can be is, the smallest is 0, and then
Now, let me draw the sine curve.
One.
So the biggest it can ever be is 1. The smallest it can ever be is minus 1. Okay? So if we're looking for extraneous solutions, I see one right there. Root 13 is at least 3. And I'm going to end up with sine of x being a number less than minus 1 if I solve it, right? So that is impossible. Sine of x can never be that number. Up here, I got minus 1/2 plus root 13 over 2. Well, what is that? That's minus 1/2 plus, if I say that that's 3.5, so, 3.5 over 2. That's also impossible. That's 1 plus. Okay, so how did I get 2 impossible solutions? It's because I gave you an equation that didn't have any solutions. There is no value of x where that would ever be true. And you can kind of see why. This can at best be plus 1. This can at best be plus 1. Well, plus 1 minus 3 is never going to be 0. So I tried to solve an equation that could not possibly be true. I made this number up just to illustrate how we would solve it using the quadratic formula. And then it turns out that the quadratic formula gives us 2 solutions that are both impossible. And I can see why.
Okay.
Okay.
Seems pretty complicated.
Well, you may not get anything. I hesitated to even introduce you to that problem because you hadn't given me any quadratics that couldn't be solved by factoring. In other words, if I make that a 2, then it's sine x minus 2 or plus 2 times sine of x minus 1. And that produces the correct middle term, so that becomes equal to 0, and one of these solutions is still impossible. Notice now what you're looking at. One of the solutions would be sine of x equals minus 2. The other solution would be sine of x equals 1. Well, this is possible, but this is not. So, however you've come to the solution, you have to make sure that it's not an extraneous solution. Remember.
Say that one more time, please.
What's that?
No, I was saying, can you say that one more time, please? I didn't hear
Yeah, no matter how you come up with your two solutions, if you're dealing with something that looks like a quadratic, you could easily have an extraneous solution, or two. In other words, I gave you one problem there where we came up with two extraneous solutions. There was no solution. And a lot of times you'll come up with two solutions, but one of them won't be possible. In other words, it's impossible for the sine of x to be equal to minus 2. So I crossed that out. That's not a possible solution. This solution occurs whenever x is pi over 2. So x equal pi over 2 would be the only solution to this problem.
Okay.
X equal pi over 2. It has one solution only.
Since you just factored it.
Just factored it because it was very factorable. In other words, as long as it's factorable, I could have also used the quadratic formula on that. I would have come up with the same solution. The only thing you have to remember if you're using the quadratic formula that gets people really screwed up is it's not x equal anymore. It's sine of x equal. Okay? You're familiar with e to the x?
No. I've heard about it, but not anything recent.
Here we have a quadratic in e to the x. Why? Because this term is the square of that term. That's all I need. So if I wanted to factor this quadratic and it was factorable, well, it would be e to the x plus 2 times e to the x minus 1. Notice that e to the x times e to the x is equal to e to the 2x. So when you're dealing with exponentials, you add the exponents. So it's a little hard when you first see this the first time to realize that you're looking at a quadratic, but that's exactly what it is. And now I can solve it easily. Where is e to the x equal to minus 2? Or where is e to the x equal to plus 1? Well, this one's actually impossible. E to the x cannot be equal to minus 2. But e to the x can be equal to plus 1 when x equals 0. So 0 is the only solution to that. Now the only reason I show you this is to show you that quadratics can come in all kinds of different forms. They can come as polynomials, x's. They can come as trig function, sine squared x, cosine squared x. Or they can come as exponentials, e to the 2x plus e to the x. And you could also, let me make that 3 again. I could use the quadratic formula to solve that equation. And what's going to go on the left side is not going to be x. What is it going to be? E to the x would be equal to minus b plus or minus the rest of it.
So you just adapt whichever variable you're using.
Exactly. And some people like to use substitution. In other words, for this problem here, maybe they would say, let's let x equal e to the x. I can't do that. Let's let u equal e to the x. Okay? It's a little easier to see it that way. Now, well, what's e to the 2x? That's u squared plus u minus 3 equals 0. Now, if I ask you to solve that, you're solving a polynomial. In other words, you're going to use the quadratic formula, but it's going to be u equals minus b plus or minus. And then when you're all done, replace the u with e to the x. So you end up with e to the x equals those two things.
Okay.
All right. I've probably told you way more than you need, just because I'm not sure you're going to encounter anything like that, where they give you a trig quadratic that can't be solved by factoring, where you would have to use the quadratic formula.
Okay. Another problem.
Yeah, we got 10 minutes here. We got time for another one.
Hold on 1 second. I guess it would be sine squared x plus cosine squared x.
Did you say sine squared of x plus cosine squared x?
Yeah. And this is from like this is that we've been doing before.
Is this an equation you're giving me?
Yes.
Where's the equal sign? What's on the other side of it?
No equal sign. It's sine squared x plus cosine squared x.
So it's
And it
just
says trig identity expression.
they want you to substitute an identity for that.
Correct.
What is that equal to?
Couldn't I do the sine squared x?
Always 1. That is your very first trig Pythagorean identity that you want to memorize. That is the most important one. No matter what x is, that is always 1. X can be 30 degrees, 45 degrees, 79 degrees, 364 degrees, doesn't matter. That's always 1. Okay? What are your other 2 trig Pythagorean identities? The first one starts with this. What's the rest of it?
Tan squared x minus 1.
Plus 1.
Or plus 1.
Equals?
Sec, or secant. Squared x.
Now, if you can memorize this one, the third one is quite easy, because the third one is the same as the second, only using cofunctions instead of the functions. So what's the third one?
Secant minus 1.
Hold on. What's the cofunction of tangent?
Oh, sine over cosine.
No, the cofunction is cotangent.
Cotangent.
Yeah, you get cofunctions.
Oh yeah.
Just substitute the word co in front of the function.
Yes.
Okay. So the cofunction of tangent is cotangent. What's the cofunction of secant?
Cosecant.
So this one you don't really have to remember. You just have to remember that it's the same as the second, only using the cofunctions. And I like those little tricks, because there are 11 trig identities that you absolutely have to memorize. The 6 reciprocal ones, the 3 Pythagorean ones, these 3, and the 2 quotient ones. The quotient ones being this and this. Well, you certainly have to remember this, but this one is just the reciprocal. As long as you remember cotangent is reciprocal to tangent, don't really have to store that in your memory banks anywhere. So you can take your 11 vital trig identities and narrow it down to 6. There's only 6 that you absolutely have to memorize. And that's the first 3 reciprocal, because the second 3 reciprocal are obvious. In other words, if sine is equal to 1 over cosecant, well, the second one, we know cosecant must be equal to 1 over sine. You don't need to memorize that one. Okay? But you do need to memorize the other 2. In other words, cosine equals 1 over secant, and tangent equals 1 over cotangent. So you do have to memorize those 3, and then those will produce the other 3. So those are your 6 reciprocal identities. Here's your 3 Pythagorean identities, and there's your 2 quotient identities. Those 11 you want to know by heart. And rapidly. You don't want to have to think about them. They will introduce you probably. You haven't had to verify trig identities yet, have you?
I don't know. Can you show me a problem or explain it? Just so I can.
In other words, if I said to you that tangent of x minus 1 equals sine over cosine minus 1. Well, I'm telling you that this is an identity. The left side is identical to the right side. How do you prove it? By turning the left side into the right side. Well, by substituting sine x over cosine x for tangent, now I have the exact same as the right side. So I have verified a trig identity.
Yes, I've done that.
Okay, well, the only purpose in verifying trig identities, the only reason they spend a couple of days on that, is because it is excellent practice for you to memorize your 11 basic trig identities. In other words, if you do some of these for like an hour, by the end of that hour, you'll know exactly what your trig identities, all 11 of them are. You won't even be able to help yourself. So it's excellent drill. It's excellent practice for memorizing your 11 trig identities, is to do a lot of verifying or proving trig identities. There's a few more tricks to doing it other than just knowing your 11, but that's the primary thing, is to know your 11 identities. And you'll find that it makes it much, much easier to verify trig identities as long as you are, Johnny on the spot with those 11 identities. You want to know them, you want to know them without having to look them up. If you have to look them up, it's not going to be very helpful because you won't know which one you want to look up. That's the beauty of verifying trig identities, is it forces you to memorize them. You will not be able to get by having a cheat sheet and looking them up. That won't work.
Okay.
Okay. All right, Taylor. I will let you go.
Okay. Sounds good.
And good luck on your quiz tomorrow.
Thank you. I'm probably going to set up another session for my test practice, too.
Okay. Sounds good.
Okay.
Talk to
See you soon.
Bye-bye.